Hi folks, Mr. Long here. I'm going to do a screencast on related rates, and it's a form of, it's related to the chain rule. In fact, the entire thing is focused on the chain rule. But first, there's something in the logs and exponential unit that we did that I think people found confusing, that every time we differentiated y, we would write y prime, and I think some people weren't sure why that occurred, and I own that, and I'm going to explain it in a little bit more detail right now. And the way I'm going to do that is I'm going to start with just a little example over here. I'm going to say, oh, whoops. I'm going to say y equals x squared over here. So if I'm going to differentiate this, right, if I have y equals x squared, I know I've got this parabola here. This is y and this is x. And I'd be getting the slope on this at that point instantaneously, right? So delta y over delta x, which is when it's instantaneously, when that delta is really small, it's dy by dx. So when I differentiate y, I write dy by dx, because that's the slope, equals 2x. And that's what we do to determine the rate of change of y with respect to x. So we've got y on this axis and x on this axis. Now, on the other hand, what if I'm writing my function this way, x equals y squared? Well, that's very different, right? That's like saying that you've got x up here and y down here. You could be writing it that way, right? If you had an inverse something. But if I'm going to differentiate just x by itself, then the derivative of x is 1. But if I'm saying that that y is a function of x, then instead of, like over here, oh, by the way, folks, y prime is just a short form for dy by dx. So if I'm going to differentiate x, then I'm actually doing dx by dy, right? Okay, and then that's going to equal 2y. So dx by dy would equal 2y. Now, that still hasn't got to our, if we differentiate y, we have to write dy by dx. But let's take a look at this. What if I want to get rid of that? Well, I would have to multiply both sides by dy by dx, dy by dx. And then that would cancel out dx, dx, dy, dy. So I'd end up with 1 equals 2y dy by dx. Okay, so, and that's the mathematics of why it works. So if I was to start back here again and go x equals y squared, instead of going through this whole thing where I write dx by dy, instead I can just write the derivative of x is 1, and then I write the derivative of y is 2y, but I have to write dy by dx because I've differentiated y. Okay, and then I get the same result without having to multiply both sides by dy over dx. Okay, so hopefully that helps a little bit. So every time you differentiate y, you write dy by dx. And it depends, again, on what variables you're working with. All right, so let's move on. So here's our first problem that we're going to work on. Okay, the first problem that we're going to work on is in a related rate. So I want you to think about what that means, a related rate. And we've already done this a bit when we looked at, for example, when we started the chain rule, what we did was we looked at, specifically, we looked at things like a square was growing. And so when the square was growing, there were 3 things happening. The area was growing, the length was growing, and the time was growing. So we had to have a relationship between those rates. And in fact, you had that on your test. Okay, so let's take a look at this. So let's look at our problem. Okay, what's happening here, and what do we want to figure out? So here's a car going across the screen, right? So you can see that car going across the screen. And what we're going to try and figure out here is, the car is coming across here, and we're going to assume it's driving at 80 kilometers an hour, okay, across there. And this distance from here to here, this is an intersection, by the way, right here, and this distance from here to here is 2 kilometers. Okay, that's 2 kilometers. This distance from here to here is 3 kilometers. And we want to find out how quickly this distance here, the distance from the house to the car is changing when it gets 3 kilometers to the right of the intersection. Okay, so it's driving along here at 80 kilometers an hour, constant speed. That distance is 2 kilometers. And what is that rate of change of distance? So how is the hypotenuse lengthening? What rate is the hypotenuse lengthening when it's at 3 kilometers? Okay, so what we're looking at really is this little triangle right here. To 3, and then like so. And you'll see when it gets to that point, right? You're going to see how that triangle works. Okay? So that's what we're trying to figure out. What's the rate of change of distance from the house to the car when the car is 3 kilometers to the right of the intersection? So now we're going to work through this. And again, hopefully I really encourage you to print this out if you have a chance. And then you can fill this in as you go through it. And the steps that we take for these related rates questions are always the same. What I'm working through right now is the first type of problem we're going to look at, the Pythagorean theorem. Once again, I'm doing these a little bit differently this year than I have in the past. I'm doing a non-traditional approach to this that will reinforce your understanding of the chain rule. And so if you see solutions and things online, they might look a little bit different. This is done, the way I'm doing it right now is done in other parts of the world, but not necessarily in Canada and the US. Okay, so here we go. Let's work through this problem. So we want to find that rate of change. So I'm going to look at the diagram here. What we're trying to figure out is how quickly is, and if I label these, right, this is going horizontal, so we'll just call that distance x. This distance is up and down, I'll call it y. This third dimension I'll call z. And what we're actually trying to figure out is, what is z? Okay, what is dz by dt? How quickly is that distance changing with respect to time? That's the question, that's our goal. And recognizing that we're at an instant when we're exactly 3 kilometers away past the intersection, and then the car is moving at a rate of 80 kilometers an hour. Okay, so let's draw a diagram now. First step always is draw a diagram with variables. So like so, just like we did up there. This right here is y, and it's equal to 2. This is z, and it happens to be equal, oops, not z. That's z, and it's not z. This distance is x, and it happens to be 3. We're going to call this distance z, and we don't know what it is. Now, one of the things, I should say variables and constants there, I guess. I'll probably edit that before I put it in your handout. So we have to know what's a variable and what's constant. That's really important because things that are constants, the rate of change will be 0. So let's look at what it is. And I really think what we should do is put a C down for things that are constant and a V down for things that are variable. Okay, or even CON and VAR. So let's look at this. Y equals 2. Does that change or not change? Well, that's the distance from the intersection to the house, right? That's the house. So that distance never changes. That is constant. It never changes. This x equals 3. That's the distance of the car from the intersection. That's always changing. That is variable. And this z, this distance from here to here, that's also variable. It's always changing as well. So that's variable. That's important to be able to do that. Okay, so now let's go through and look at our rates. So what's our goal rate? What do we want to figure out? We want to figure out the rate of change, dz by dt. That's the goal, right? How quickly is that distance from the house to the car changing? Now, what about this right here? Do we know a rate there? Yeah, it's given. dx by dt is 80 kilometers an hour, right? And I should put diagram of variables, constants, and rates. So I should have put all of those on there. So our goal, what we want to figure out is dz by dt. But we should also write down what rates are given. What rates are given? Well, the given rate is dx by dt. And we can tell by looking at the units, right? Kilometers per hour. And so the given rate is 80 kilometers per hour. So the nice thing about this is we can always write our rate with the chain rule. So this is our goal. So we're going to have dz by dt. And then I'm going to need at least two other rates to work with to build that with the chain rule. So what do I have to work with? Well, I have dx by dt right here. So how does that match up? I've got dt in the bottom and dt in the bottom. Well, that's a good thing, okay? Because sometimes you'll have to flip this rate. For example, if it was dt on the top, then I'd have to flip it. If it was dt by dx, then I'd have to flip it to dx by dt. So I've got dx by dt, so I'm going to write that right away. Dx by dt, that's helpful. But remember, I need to get dz by dt. So I need to introduce in the top dz. Now, what do I need to introduce in the bottom? Well, I need that dt and I need that dz, which means I have to get rid of dx. So that's a dx there. So those will eventually cancel out. Okay, so that's my chain rule relationship. Now, what I have to think about is that I have this. That's given. That's 80 kilometers an hour. I just need to figure out this, dz by dx. But let's be careful. What does that actually mean? That means I need to get a relationship like this, where z is on the y-axis and x is on the x-axis. So I need to write an equation, z equals some function of x. How am I going to do that? That's our next part. So what equations? Now we understand rates, we understand the diagram. Well, if you see a picture like this, what's the governing equation going to be? It could be right-angled trig, or the other thing it could be is Pythagorean theorem. So what is our relationship for the Pythagorean theorem for this? Well, it's just going to be x squared plus y squared equals z squared. What's really important here is that we note the constants, and we put in the constants because the derivative of a constant is 0. So what are the constants in this case? Well, the only thing that's a constant is y. Y is worth 2. So that means that our equation is x squared plus, that's going to be 2 squared, right, which is 4, equals z squared. Okay, so that's our governing equation. Now I need to write it in terms of z. So I have to start with z because I'm needing to get dz by dx, right? So I'm going to write z squared equals x squared plus 4. But I need to differentiate to get dz by dx. Okay, dz by dx. So remember, I can just differentiate this. Okay, sometimes you're going to see solutions where they isolate, they go z equals the square root of x squared plus 4. I think that's probably very inefficient. Oh, I apologize. One of our dogs is barking. Hopefully you can't hear that too loud. So I wouldn't do this. I would just do, again, what's called implicit differentiation. Let's differentiate z. And then I've got x on this side, so it's going to be dz by dx. So what's the derivative of z squared? Well, it's 2z. But then I have to write dz by dx because I've differentiated on the left side. And that's going to equal 2x. Okay, that will equal 2x. And the derivative of 4 is 0. So finally, I can see that there's a 2 on both sides, so those divide out nicely. And I need to isolate for dz by dx. So dz by dx, I need to divide both sides by z. So I'm going to end up with dz by dx just equals x over z. Okay, that's what that's worth. So now we come down and we have to determine any missing variables. So what I should do here is write down the chain rule that I started with. So dz by dt was my goal. And that's going to equal dx by dt multiplied by dz by dx. And I substitute things in. So I'm going to substitute in dx by dt, and that was 80 kilometers an hour. Oops, I don't need to circle that, do I? And then I need to multiply by dz by dx, and that worked out to, nice and simple, x over z. And that's x over z. And given our scenario, do we know x and z? So this part 4 here is determine any missing variables or constants as needed. So do I know x? Yeah, I definitely know x. X was given as 4. But I don't know z. Z is a question mark. So how do I figure that out? Well, z, I know that the relationship is, I already figured that out. Z squared is x squared plus 4. So z squared equals x squared. X is worth, oh, x is not 4, x is 3, sorry. So x is going to be 3 squared, or z squared is going to be 3 squared plus 4. 3 squared is 9. 9 plus 4 is 13. So z squared equals 13. And z will equal root of 13. Okay, so now we know all of our values. Last step that I have to make here is to substitute all the values in. dz over dx equals dx by dt, which is 80 kilometers an hour. And then I multiply that by x over z. And what is x over z? Well, oh, that should be dz by dt. Sorry, folks. Once again, I'm making a mistake here. 80 kilometers an hour multiplied by x, which is 3 kilometers, and z, which is root 13 kilometers. Now, what's nice about this is you can always check your units, because remember when we did the chain rule, our units came from there. So z is measured in kilometers, t is measured in hours, and I look and I can divide those kilometers out, and what I'm left with is kilometers per hour. Okay, so I can write this in exact form as 80 times 3, which is 240, and that's in 240 divided by root 13 kilometers per hour, which I think simplifies to something like 66 kilometers per hour, but you'll have to double check that. And that, folks, is dz by dt. That's how quickly the distance is changing as you go through, from between the house and the car. So let's look at that. These problems are all tackled the same way. Start by analyzing the diagram if it's given, or creating a diagram if it's not given. You want to note that what you're noticing is what's a variable, what's a constant. But label everything with letters, every dimension on your diagram. Then you're going to develop the chain rule relationship that's going to allow you to get the answer. Okay, try if you can to isolate it, but you won't always be able to do that. Certain types of problems will lend itself that way, certain problems won't actually, so I shouldn't say that as a general rule. Then you look at what's your governing equation for your situation. Maybe it's volume, maybe it's area, maybe it's similar triangles. There's lots of different things that it can be. Here it's Pythagorean theorem. And then what you want to do is, if there's any values missing that you need, you figure those out. Usually it comes from your diagram and your equation, your governing equation. And then lastly, you substitute everything you know now into the chain rule to get your needed rate. Okay, so you're always solving for a rate with these. All right, hopefully that helps, folks. I know that's a long screencast, but I'm hoping it'll be really helpful. And good luck in your homework.